Hello everyone. Uh, Welcome to the week 6 tutorial session of Thermodynamics course. I am Thananga Sutia, and today we will be doing problems related to one of the very important cycle in thermodynamics, that is basically the Carnot cycle. So we have done questions related to Carnot engines also, but here we will be doing a much more detailed and complicated questions which will be useful for you in solving the assignments as well as in competitive examinations like gate and all. Okay, so let me share it. Okay, yeah. Okay, so the first question is the efficiency of a Carnot heat engine working between two temperatures is 60%. Now, if the temperature of the source alone is decreased by 100 Kelvin, the efficiency becomes 40%. Define the temperature of the source and then that of the sink. Okay. Yeah. So you have to find the temperature of the source and of the sink. So what it is telling. Okay. So this T1 is my source temperature and T2 is my sink temperature, and say this is my heat engine, which is basically a Carnot engine. So it will absorb some Q1 amount of heat, will do some amount of work, and will release some Q2 amount of heat to the thermal energy reservoir at T1. Okay, so what it is telling that initially when the Carnot heat engine was working between these two temperatures, then the efficiency was 60%. Okay, so we know that efficiency is equals to output by input. Okay, and here the output is basically your work done and the input energy is your Q1. Okay, now from energy conservation we can show that W is nothing but Q1 minus Q2, and that will be divided by Q1. Now if you further simplify it, we will get this one as 1 minus Q2 by Q1. This formula is valid for all the heat engines. It should not be Carnot engine, it can be any heat engine. This formula is valid. Okay, now whenever it becomes a Carnot, for Carnot or reversible heat engines, for Carnot engine, for Carnot engine what happens that the ratio of the heat reservoirs released by the heat reservoirs is equal to the temperature of the ratio of the temperature of the reservoirs. Okay, so this means the eta Carnot can be written as 1 minus T2 by T1. Okay, so now then your first case, what it is telling us that for first case what we are getting this one as 1 minus T2 by T1 is equals to 0.6. Okay, this is my equation number 1. Okay. Now second case, in the second case what happens that you are decreasing the temperature of the source. Okay, the temperature of the source you are decreasing by 100 Kelvin, and then the efficiency becomes 40%. That means in the second case 1 minus T2 by T1 minus 100 and this will give you 0.4. Now if we solve, we have two equations, we have two unknowns. If we solve these two equations, we will get the value of T1 and T2. Okay. So 1 minus T2 by T1 is equal to 0.6. Okay, so from here I can get T2 divided by T1 is basically your 0.4. Okay, equation 2, it tells us 1 minus T2 divided by T1 minus 100 is equal to your 0.4. Okay, now this will be just a simple mathematics. T2 divided by T1, I am dividing both the numerator and denominator by T1. This will be 1 and this will be 100 by T1, and that will be equal to your 0.4. Okay, then in the next step I can put T2 by T1 from equation 1 or from equation 3, if I name this at equation 3. So from equation 3 I can get that this will be 0.4 divided by 1 minus 100 divided by T1 is equal to 0.4. Okay. Further what I can do is that so if I take the LCM, 1 minus 100 by T1 minus 0.4, this will be equal to your 0.4 into 1 minus 100 by T1. Okay, so this one is also 1 minus 100 by T1, this one is also 1 minus 100 by T1. I can take this to this side, so this will be basically 1 minus 0.4 times 1 minus 100 by T1 will be equal to 0.4. Then this will be equal to 0.6 into 1 minus 100 by T1 will be equal to 0.4. Then I can write this one as 1 minus 100 by T1 will be basically equal to 0.4 divided by 0.6. Okay, so this one I can write as 1 minus 4 by 6 is equal to 100 by T1. So this will be basically 2 by 6 is equal to 100 by T1, and then I can write T1 is equal to 100 into 6 divided by 2, that is your 300 Kelvin. So this is my source temperature. Now we know again that T2 divided by T1 is equal to 0.4. So therefore T2 will be equal to 0.4 times T1, which is nothing but 300. So that will be equal to 120 Kelvin. So this is my sink temperature and this is my source temperature. Okay, If you have any doubt, you can ask. Okay, now let us move to the next question. Suppose that two heat engines are connected in series such that the exhaust of the first engine is used as heat input to the second engine. The efficiencies of the engine are eta 1 and eta 2 respectively. What is the net efficiency of the comparison combination, and compare this efficiency with eta 1 and eta 2. Okay. Yeah, so you have two heat engines. Okay. This is one heat engine, this is another heat engine. Okay, you take q1 heat, you do w job, and you eject q2. Okay, now what happens, whatever you eject, that is used as heat input to the second engine. It will do some w2 amount of job, and rest all q3 will be released. Okay, so if I am taking this temperature as T1, this temperature is T2, and this intermediate temperature is T, then it is telling us that the efficiencies of the heat engines are eta 1 and eta 2. So my eta 1, and remember they are not saying this as Carnot engine, so you cannot write this in terms of 1 minus T2 by T1. Okay, so my eta 1 will be basically equal to W1 by Q1, which we also know we can write this one as 1 minus Q2 by Q1. Okay, and my eta 2 is what? My eta 2 is basically W2 divided by Q2. Okay, and what is my W2? My W2 is basically Q3, Q2 minus Q3 so this will be also equal to 1 minus Q3 by Q2. Okay, so this is my eta 1, this is my eta 2. Now you have the combination. Okay, now if you combine these two as a single engine, then eta combined will be equal to what? My again output by input. Okay, now the question is, what is the output of these two combination engine? It is W1 plus W2. What is the input? Remember, Q1 was the input to the first engine, then it rejected some heat amount Q2, it done some work W1, and then that Q2 was only used in the second engine. So whatever is there, the combined heat engine, both the heat engine, if you combine as a single engine, then also your input will be Q1, because this Q1 is the only input to the because Q2 is the input to the Q2, that is for the second engine, is basically a part of the Q1. So that's why our input is Q1. Okay, so now we have W1 plus W2. Now what we can do, we can substitute W1 and W2 in terms of Q's. Okay, so W1 will be basically Q1 minus Q2, and my W2 will be basically Q2 minus Q3. and this will be divided by Q1. So this got cancel. Now my combined is what? Q1 minus Q3 by Q1. Okay, so this can I can also write this one as 1 minus Q3 by Q1. Now then we have to express this in terms of eta 1 and eta 2. Okay, so here what we can do is that eta combined we have got as 1 minus Q3 divided by Q1. What we can write this one? 1 minus Q3 by Q2 I can do, and also yes or no, because in doing so it will remain the same. Okay, so from here Q2 by Q1 is what? Q2 by Q1 is basically 1 minus eta 1. Similarly Q3 by Q2 is your 1 minus eta 2. Okay, so what I can write, this will be 1 minus eta 1 times 1 minus eta 2. Okay, clear? Now suppose you have n numbers. This is a bit extra. Suppose now this is your answer. This is your in combination with eta 1 and eta 2. Now suppose there are n number of I should actually p, then it will be better. There are p number of heat engines connected in series, just like the first case where output of heat rejected to the sink is used as the heat input to the other engine, and so on and so forth. So in that case my eta combined will be 1 minus eta 1 times 1 minus eta 2 times 1 minus eta 3 and so on up to 1 minus eta p. Okay, this will be your answer. Clear? If you got any doubt you can ask. Okay, fine. Let us go to the next question. A heat pump, it receives energy from a source at 80 degrees Celsius and delivers energy to a boiler that operates at 350 kilopascal. Okay, the boiler input is saturated liquid water and the exit is saturated vapor, both at 350 kilopascal. The heat pump is driven by a 2.5 megawatt motor and has a coefficient of performance that is 60% of a Carnot heat pump coefficient, COP. Okay, now what is the maximum mass flow rate of the water system, the system can deliver? Okay, so let us first see. I will draw the heat pump. Okay, so this is my heat pump. What it does, it receives energy from a source at 80 degrees Celsius. Okay, so this one is my 80 degrees Celsius. Okay, it receives say Q2 amount of energy. Okay, then it delivers energy to a boiler. So now what it does energy to one reservoir, and this reservoir is now a boiler. Okay, and this boiler is at 350 kilopascal. Okay, this boiler is at kilopascal and say it delivers energy Q1. Okay, now the boiler input is saturated. Now since this is a boiler, the work it will be to produce steam. Okay, so say, and let me change the color. Yeah, say there are some water input, okay, which goes inside the boiler and comes out. Okay, so what it is telling that the input, boiler input is saturated liquid water. So whatever goes in, this is basically your H2O in liquid state, saturated liquid, and whatever goes out, that is basically your gaseous state. There is no superheated state. Okay, that is just change of phase from the liquid to the gaseous. Okay, this is the boiler takes Q1 amount of heat, and this Q1 amount of heat is used to change the phase of this liquid water, saturated liquid water, to saturated gaseous water. Okay, and this change phase process, it takes place at 350 kilopascal. Okay, now this heat pump, it is driven by 2.5. So this heat pump, it carries energy from low temperature to high temperature. So according to second law, it will require some amount of work, and this work is basically your 2.5 megawatt motor. Okay, now it has a COP, that is 60% of that of a Carnot heat pump. Okay, now whatever, if this would have been a Carnot heat pump, whatever would have been their efficiency, it is the 60% of that. Now we have to find out the maximum mass flow rate. Okay, now first of all, what we need. Okay, so we need Q1. Okay, and what is this Q1? This Q1, it is basically used to convert this liquid water to gaseous water, saturated liquid water to saturated gaseous water. So what we have to go, so we need to see steam table, and we need to see pressure part. Why? Because this phase change pressure part, we know 350 kilopascal, and we have to check what is the amount of enthalpy change when at 300 kilopascal it changes to from saturated liquid to saturated vapor. That means at 350 kilopascal, we need to check HFG. Okay, one more thing, since the direct COP is related to Carnot heat pump COP, and Carnot heat pump COP, it requires temperature of both the reservoir, that is low temperature reservoir and high temperature reservoir. We know the temperature of low temperature reservoir. What will be the temperature of high temperature reservoir? The temperature of the high temperature reservoir will be nothing but T1 will be nothing but T saturation at 350 kilopascal. Yes or no? Because phase change is taking place here, phase change is taking place, and phase change will take place at a constant temperature and pressure. Yes or no? And 350 kilopascal is saturation temperature once it is reached. Okay, let me draw the TS diagram if you forgot in the last class. Okay, so this is suppose, and say this is my 350 kilopascal line. Okay, now we need this temperature, this saturation temperature, because it goes from this state to this state. Okay, we basically require this amount of energy. Okay, so that's why we are calculating this saturation. So we have to go back to our steam table. Okay, and we have to see 350 kilopascal, and remember that this steam table, it is in megapascal, so basically we have to see 0.35 megapascal. Okay, yeah, so this is my 0.35 megapascal, and here my T saturation is 138.857 degrees Celsius. Okay, my T saturation is 138.857 degree Celsius. And one more parameter we require at this is the HFG. Okay, so this is my VF, this is my VG, this is my UF, this is my UG, this is my HF, this is my this is my VF, this is my VG, this is my UF, this is my UG, this is my HF, this is my HG, this is my HFG. So it is 2147.7. okay, 2147.7, 2147.7 kilojoule per kg. Okay, so this HFG we will be used in calculating the Q1. So that means okay, now what will be the COP? COP will be output by input. What is my output? My output is Q1, because this Q1 is my desired output for a heat pump, yes or no? And this is my WC. Now I know WC, but I don't know Q1. Okay, now what is Q1? This Q1 amount of heat is only used to this is basically HFG times mass flow rate. Now why I am multiplying it as mass in terms of mass flow rate? Because this is kilojoule per kg. Now if I will multiply with kg per second, I will get this one in terms of kilowatt. Okay, kilowatt. Okay, so this will be basically m dot into 2147.7 kilowatt. Okay, this is the COP. Now I will put it here. This will be basically m dot into 2147.7, and the WC, it will be 2.5 megawatts. So I will convert this into kilowatt into 1 10 to the power 3. Okay, so this is done. Now again, the COP is 60% of a Carnot heat pump. So COP Carnot, and we know this is basically your T1 divided by T1 minus T2. Now if you forgot, let me just quickly derive it. Okay, so that will COP was what? Q1 by WC. Okay, and my Q1 by Q1 minus Q2. Okay, and then again this is Q1 by Q2, Q1 by Q2 minus 1. Now for reversible Carnot cycle, this Q1 by Q2 is basically T1 by T2. Okay, T1 by T2 minus 1. So this was what? T1 by T1 minus T2. Okay, so here we can put it, eta Carnot is what? COP Carnot is equals to your T1 by T1 minus T2. Now our COP is what? COP of our heat pump is what? 60%, that is 0.6. Is it 60%? Yeah, 0.6 into T1 by T1 minus T2. Okay, so now we have got everything. So COP is equals to your from this equation we have got this one. Okay, and from this equation we have got COP as this one. Now we'll just put this two as same. So what we'll get from 1 and 2, 0.6 into T1 by T1 minus T2 is basically your m dot times m dot into 2147.7 divided by 2.5 into 10 to the power 3. Okay, so 0.6 into what is my T1? Okay, I got T1 as 138.85 degrees Celsius. So if I convert this into Kelvin, that 138.857 plus 273, 411.857, 411.857 Kelvin. Okay, so this will be 411.857 Kelvin, and you know, I think that the temperature difference, whether you express it in degree Celsius or degree Kelvin, it remains the same. Okay, so this will be basically your 138.857, 138.857 minus 80. Okay, and this will be your m dot into 2147.7 divided by 2.5 into 10 to the power 3. Okay, so now you just have to do these calculations and you will get the answer. 411.87 to 10 to the power 3 divided by 138.7 minus 80 into 2.477. So I am getting my answer as 4.8872 kg per second. Okay, any doubt you can ask. Okay, let us go to the next question. The efficiency of a Carnot cycle can be increased either by increasing T1 or by decreasing T2. Which one is more effective? So from the previous questions we have already got that eta Carnot is basically your 1 minus T2 by T1. Now this eta, it can be increased if we decrease T2 or if we increase T1. Okay, now which one is more effective? Okay, that means if you increase T1, will it increase more, or if you decrease T2, will it increase more? Okay, so let us do some cases. Okay, say your first case, let T1 be increased by delta T. Okay, keeping T2 constant. So then for the first case, eta 1 will be your 1 minus T2 divided by T1 plus delta T. Okay, this is my case 1. Now let me do the second case, that let your T2 be decreased by delta T, keeping T1 constant. Okay, so then in that case my eta 2 will be 1 minus T2 minus delta T divided by T1. Okay, now we need to compare whether my eta 1 is greater or eta 2 is greater. Okay, so let us do subtraction of eta 2 minus eta 1. Okay, 1 minus T2 minus delta T by T1 minus 1 plus T2 divided by T1 plus delta T. 1 got cancelled. Now what it remains, eta 2 minus eta 1 is your T2 by T1 plus delta T minus T2 minus delta T divided by T1. Okay, take the LCM, it will be T1 into T1 plus delta T. Okay, this will give you T1 T2 and this will give you minus T2 minus delta T times T1 plus delta T. Okay, then you will get here T1 T2 minus, put everything this one, T1 T2 plus T2 delta T minus T1 delta T minus delta T squared divided by T1 into T1 plus delta T. Okay, we remove the brackets, T1 T2 minus T1 T2 minus T2 delta T plus T1 delta T plus delta T squared divided by T1 times T1 plus delta T. This got cancelled, so if you take delta T common, this will be delta T times T1 minus T2 plus delta T squared by T1 times T1 plus delta T. Now see, this term is positive, delta T whole square is positive, T1 plus delta T is positive, T1 is positive, delta T is positive. Now, so what it will happen, it will depend on this difference. Now we already know that T1 is greater than T2. Now since T1 is greater than T2, okay, therefore what I got, eta 2 minus eta 1 is greater than 0. That's why I got eta 2 is greater than eta 1. Therefore, what was my eta 2? My eta 2 was basically decreasing T2, keeping T1 constant. So, decreasing T2 is more effective than increasing T1 for increasing the efficiency of a Carnot cycle. Okay, so what we did, we have calculated the eta, that is the efficiencies for both the cases. We have subtracted and we have got that the second case efficiency was greater than that of the first case. That's why that second case, that is the decreasing T2 is more effective than increasing T1 for increasing the efficiency of a Carnot cycle. Okay, now let us go to the next question. In a Carnot cycle, the lowest pressures and temperatures are equal to 1 bar and 20 degrees Celsius, and isothermal compression pressure is 4 bar. Pressure after isentropic compression is 10 bar, and after heat addition process is 5 bar. You have to calculate the highest temperature of the cycle, the change in entropy during the isothermal expansion, the heat addition to the cycle, the heat rejected by the cycle, the power developed with 150 cycles per minute, the thermal efficiency of the cycle, and the mean effective pressure. And you have to assume that gamma is 1.4. Okay, in order to do that, you have to understand how a Carnot cycle looks. So I will quickly show the PV and TS diagram for a Carnot cycle. Okay, so if this is my TS, this is how a Carnot cycle looks. Okay, so there are 4 processes basically, out of which 2 are reversible isentropic compressions, and the other is reversible isentropic expansion, and the opposite one is that two isothermal processes are there. In one case isothermal expansion takes place, in other case the isothermal compression takes place. Okay, so this, if you want to see in the PV diagram, okay, in PV. Okay, now before that, let me show you what is 1 to 2 basically. So 1 to 2 is your isentropic, and I think you know by this time isentropic means reversible adiabatic. Reversible adiabatic. Okay, so that is basically your isentropic compression and 2 to 3 your isothermal expansion. Okay, 3 to 4 is your isentropic expansion, and 4 to 1 is isothermal compression. And we know that whenever we compress, pressure increases and volume decreases, and whenever it expands, the opposite happens, that is volume increases and pressure decreases. Okay, so 1 to 3 is isentropic compression, and isentropic is adiabatic, and adiabatic slope is higher than isothermal slope. So how in a PV plot it will look? Say this is my 1 to 2. Okay, then isothermal expansion like this. I'm sorry, expansion, so pressure will decrease. Okay, then again the same slope, since the gas is the same, so the slope won't change of these two lines, and similarly since the gas is the same, so the slope won't change for these two lines. Okay, so this is for a PV and this is for this one. Now that's why you have to if in question it gives you the lowest pressure and the highest pressure, or lowest temperature or highest temperature, these things are given, then you have to first plot both the PV and the TS diagram, then only you can understand, oh, what are the values they are given. Okay, so now it is telling us that the lowest pressure is given to us. Now in this all these cases, what is my lowest pressure? My lowest pressure is P4. That's why P4 is equal to 1 bar. Okay, then lowest temperature is given to us, and lowest temperature is 20 degrees Celsius, and you can see in the TS plot the lowest temperatures are T1 and T4. okay, because 1 and 4 1 to 4 sorry 4 to 1 is an isothermal, so whatever temperature is in 4, that is same in the temperature, that is in same in the point 1. So T1 is equals to T4 is equals to basically your 20 degrees Celsius. Got it? Then isothermal compression pressure is 4 bar. Okay, so where is the isothermal compression? Isothermal compression is 4 to 1. Okay, that means P1 is given to you as 4 bar. Okay, done. Pressure after isentropic compression is 10 bar. Okay, after isentropic compression 1 to 2 is isentropic compression, so P2 is given as 10 bar. Okay, then and after heat addition, okay, where is the heat addition taking place? See, entropy increases from 2 to 3 and entropy decreases from 4 to 1. So heat addition can take place only from 2 to 3. Okay, because if we know if we add to the system, entropy increases. Okay, so now the after that means this is basically your P3. Okay, and your P3 is 5 bar. These are the given parameters. Now you have to calculate the highest temperature of the cycle. And what is the highest temperature of the cycle? It is either T2 or T3, whatever. If you find T2, it is basically T3 only. Okay, so let us start the calculations. Highest temperature of the cycle. Okay, so basically what we need to calculate, we need to calculate either T2 or T3, both are same. Okay, now here I will put some terms. This is work of expansion, I am giving it as W324, and this is work of compression, I am giving this terminology as W122. Okay, and this heat addition will take place at this point, so I am giving this terminology as Q223, and here the heat rejection takes place, so I am giving this term as Q421. Similarly, everything is here, I will not draw the same, so the same thing you can also show in that part. Okay, now the highest temperature is either T2 or T3. Now we have T1, we have P1, we have P2, but we don't have T2. So we know, see, we have P1, that means 1 to 2 processes, we know 3 parameters. Okay, so we just need one more parameter. Now we know that this process is what? It is a reversible adiabatic process, and for a reversible adiabatic process, PV to the power gamma is equals to constant. Okay, PV to the power gamma is equals to constant. So applying this and ideal gas equation, we can show that now we don't need volume because volumes are not given, we only need the pressure and temperature relationship. So we can easily derive that P2 by P1 to the power gamma minus 1 by gamma is equals to your T2 by T1. Okay, very simple. Out of this you know P2, out of this you know P1, out of this you know T1, you just need to find T2. Okay, so from here your T2 will be T1 times P2 by P1 to the power gamma minus 1 by gamma. Okay, and what is your T1? Your T1 is 20 degrees Celsius, that is 293. Okay, and what is your P2? I think P2 is given as 10 divided by 4. Gamma minus 1 is 1.4 minus 1 divided by 1.4. This will be in Kelvin. Okay, so if you can do the calculations, what you will get is you will get your answer as 380.68 Kelvin. Okay, very simple. Now moving on to the next part. So this one is done. The change of entropy during isothermal expansion. Okay, delta S during, what is my isothermal expansion process? My isothermal expansion process is 2 to 3. Delta S during process 2 to 3, that is, in bracket you have to calculate S3 minus S2. Okay, now this 2 to 3, this process is basically a reversible isothermal process. Okay, reversible isothermal process. So whenever there is a reversible process, we can express Q is equals to TdS or T delta S. This is valid for a reversible process. Why this is a reversible isothermal process? Because this is a Carnot cycle, and in Carnot cycle all the processes are reversible. Okay, so from here what I can write it as Q2 to 3 is nothing but T into S3 minus S2. So from here S3 minus S2 will be equal to Q 2 to 3 divided by T. Now just we need to find out what is the Q2 to 3. Okay, now let us apply first law of thermodynamics. Okay, Q,
Carnot cycle.
yeah,
As the efficiency equation Carnot cycle.
pardon.
So what is the efficiency? How to find out the efficiency of Carnot?
Sorry, I can't hear you. Can you please speak it clearly? I can't hear you.
So how to find efficiency of Carnot cycle?
Efficiency of Carnot cycle. So
Yes, sir.
whatever cycle it will be given, or any engine or anything, you just have to do the output by input. Okay, so here thermal efficiency is there. Here I will do this. Just wait for it. Okay.
Okay, sir.
Okay.
Sir, this record section of this class is available.
Yeah, recording will be available. I will upload it by tomorrow morning itself. Okay, you will get it.
Sir,
Okay.
in NPTEL channel.
Yeah. In this NPTEL's not NPTEL site, you can contact those. They will upload it. We have to upload it in a separate website. And even if you don't get it, you just mail me. Okay, this is my mail ID. This is my mail ID. You just mail me. I will give you my YouTube video link. Okay.
Okay, sir.
Yeah. So yes, so now we have to calculate the Q2 to 3. Now from first law of thermodynamics, Q is what? Delta U plus work done. Actually it was delta E, but if you neglect all other forms of energy, then it will become only internal energy change. Okay, and this is W. Now in this has no any other form of like electrical energy or something work done, nothing is there. So this is basically your WPdV. Okay, that is the PdV work. Now if now since this is a gaseous Carnot cycle, because gamma is 1.4 and also nothing is mentioned about real gas, so for an ideal gas, what we know that for ideal gas the internal energy is basically a function of temperature. So if this is an isothermal process 2 to 3, so that means your change in internal energy is 0. So whatever Q2 to 3 is nothing but the WPdV. Okay, now how to calculate the WPdV? This will be basically V1 to V2 PdV. Okay, now for an isothermal process, PV is equals to constant. Okay, this is for isothermal process. Then what we can write as P1 V1, I'm sorry, this process is my 2 to 3 now. So P2 V2 is equals to your P3 V3. Okay, and this one is some constant. Okay, so what we can write this one as this will be 2 to 3 na, so 2 to 3. Okay, V2 to V3, and this P I can replace this as your constant, that this constant is say some C, so C by P, I'm sorry, P in place of P I have to put not, so this will be C by V dV. Okay, now I'm taking this constant C outside, this C V2 to V3 and dV by V. Okay, so this will be basically C ln V3 by V2, basic integration. dV by V is this one, and just what you call upper limit divided by 1. What is C? This C can be P2 V2 or P3 V2, whichever is comfortable for you. So I will first put here P2 V2 ln V3 by V2. Okay, now we know P2, but we don't know V2. Okay, so since this is an ideal gas, so ideal gas equation will also work. P2 V2 is equals to RT2. Say I'm doing all for 1 kg mass of the ideal gas. Okay, so that means in place of P2 V2, I can put this one as RT2. Fine. Then we don't know V3 and V2. So, but we know P2 V2 is equals to P3 V3. So from here, V3 divided by V2 is nothing but P2 divided by your P3. Okay, so this will be your
PV raised to N is equal to
yeah. Hello.
polytropic process.
Yeah.
Sir, PV raised to N is
PV equals to
PV raised.
I'm
It's a
sorry, not
polytropic.
you're not audible. Hello.
Hello, sir.
Yeah.
Sir, PV raised to N is equal to constant is a polytropic.
Yeah, it is a polytropic process, but here it is telling us isothermal process now, so it is PV equals to constant.
Temperature is constant.
Yeah, temperature is constant. It is telling I mean in Carnot cycle there are only two processes. One is isothermal process, two isothermal processes, and two adiabatic processes, reversible adiabatic processes. Okay, so that is your
Okay.
PV to the power gamma constant is I have already done, and now this is just PV is equals to constant. Okay.
Okay, sir. Okay.
Yeah, so now we know all these three parameters, and I think you remember the value of R for an ideal gas, that is air. It is 0.287 kilojoule per kg Kelvin. Okay, and into T2, what is your T2? You just calculated it. It is 380.68. 380.68. Basically, this is your heat only. Yeah, and into ln P3. What is your P3? 5. Sorry, P2. P2 is your 10. 10 by 5. That is ln 2. Okay, you do this 0.287 into 380.68 into ln 2. So you will get I am writing here, you will get this one as 75.72, okay, kilojoule per kg. Okay, so this is what your Q2 to 3. And remember, we have one more question where we have to calculate the heat addition to the cycle. This is basically your heat addition to the cycle. Okay, so the heat addition to the cycle is done. Okay, then we got the heat addition to the cycle. We need S3 minus S2. What we will do, we will basically divide this by the temperature. Okay, that is 380.68. okay, so let me go to another slide. Yes, so S3 minus S2, it will be basically Q2 to 3 divided by your T2. Okay, and what you got, it is 75.72 divided by 380.68. 380.68. So that will be your kilojoule per kg Kelvin. Okay, 21.68, 380. So it is your 0.198 kilojoule per kg Kelvin. Okay, so this is your entropy change. Then next question is, this is done. Heat addition to the cycle, I will write it again as I have done the calculation already. See, heat added to the cycle, heat added to the cycle is your Q2 to 3, which I have already calculated, and that is your 75.72 kilojoule per kg. Okay, next is your heat rejected by the cycle. Okay, heat rejected by the cycle, so that is basically your Q 4 to 1. Yes or no? Because this 4 to 1 process, it is rejecting some amount of heat. Now similarly, since this is also a reversible process, now I can do one thing. Why I am doing because I will show you why I am doing this. So this one I can write this one as T4 times S1 minus S4, because it is a reversible process, and Q is equals to T into delta S. Okay, now we know T4, we also know delta S. Why? Let me draw it once again. Because the Carnot cycle TS diagram, from the TS diagram of the Carnot cycle, it is clear. If this is 1, this is 2, this is 3, and this is 4, it is clear that S3 minus S2 is nothing but S4 minus S1. Okay, for a Carnot cycle, and we already calculated S3 minus S2. Okay, we need S4 minus S1 or S1 minus S4, just the negative of this. So that's why what we will do, we will put negative T4 times S4 minus S1. Okay, and T4 is basically my lowest temperature, what was given to us as 20 degrees Celsius. Okay, so this will be your minus 293 into your 0.198. So Kelvin will be getting cancelled. You will get again this one as kilojoule per kg. Heat rejected, so it is coming as automatically, by default it is coming as negative. So this one you will get as minus 58, minus 58.014 kilojoule per kg. Okay, so this is your heat rejected by the cycle. Now you have to calculate the power developed with 150 cycles per minute. Okay, so it is telling us that there are 150 cycles developed per minute. Okay, so then you have to calculate first the power developed by one cycle, then the power developed by 150 cycles. I mean how many cycles in seconds. Okay, I will do the calculation, you will understand it better. Yeah, so we are in E, power developed. Okay, so we know for first law of thermodynamics, first law of thermodynamics for a cycle, what we know that summation of all the W is equals to summation of all Q. Okay, so for one cycle. Now what we need W net for a cycle. So W net for a cycle, for one cycle, that will be basically your Q net of the cycle. Okay, and what is your Q net? You have Q added to the system, you no q rejected. Remember, the same calculations you can do by p1 v1, these all work formulas also do, but since we already know these values, we should not do much more calculations to save the time. Okay, so this will be basically your 75.72 minus 58.014 kilojoule per kg. Okay, so this will be 17.706 kilojoule per kg. Okay, so this much is the work done in one cycle. Now it is telling us that there are 150 cycles per minute. Since there are 150 cycles per minute, that means in 60 seconds there are 150 cycles, so you have to produce you have to calculate the power developed, that means in kilowatt. Okay, so that means your power developed will be basically 17.706 into 150 cycles in how many seconds? 60 seconds. So in 1 second it will be divided by 60, that will give you in kilowatt per kg. Okay, so you are getting the answer as 44.265 kilowatt per kg of the ideal gas. Okay, next is your next you have to calculate the thermal efficiency of the cycle. Okay, so this is a Carnot cycle, and in my previous questions I have already done that eta for Carnot engine is nothing but 1 minus higher temperature lower temperature divided by higher temperature. Okay, working two temperatures. Okay, 1 minus T2 divided by T1. Okay, higher temperature or lower temperature by higher temperature, and we already calculated these values. So the lower temperature was 20 degrees Celsius, equation given, so 20 plus 273, and this one we have got the Kelvin temperature, that is 380.68. 380.68. Okay, so you will get this as 0.2303, and that is equal to your, in percentage, if you want to write this one as 23.03%, or you can say that this is 23% efficient. This Carnot engine is 23% efficient. Thermal efficiency done. Now this is a bit trickier one, and since your IC engines are not taught, so I'll not go more into the details of this problem, but if you will be dealing with the IC engines or whatever car engines or bike engine, diesel and petrol engine, you will more hear about this mean effective pressure term. Okay, so what is mean effective pressure? I will just give a demo. Say you have to calculate the mean effective pressure. Mean effective pressure. Okay, and say I'm naming this as PM. Okay, so what we know that the work done for PdV process keeping pressure constant is what? If WPdV for constant pressure, integration PdV from V1 to V2, if the pressure is constant, it will be P into V2 minus V1. Okay, it will be P into V2 minus V1. Now suppose there is some effective volume swept Okay, I mean, there is some effective expansion. There is expansion. See, in the Carnot cycle, there are two compression processes and two expansion processes. So there is a net effective expansion volume. Okay, there is a net effective expansion volume, which we call as swept volume. I will not write in arrow of this one. I will just tell that so for a constant pressure process, this for any process going from 1 to 2, the work done for the process is P, that constant pressure, times final volume minus initial volume. So there is a swept volume, which is basically your net effective expansion volume. Okay, there are two compression processes and two expansion processes. So out of, you combine all those volumes and you will get a net effective expansion of the volume. Okay, that is your basically your swept volume. So corresponding to that, there will be some constant pressure. Okay, suppose if the entire Carnot engine is replaced by only one process, which is a constant pressure process, and that constant pressure you are maintaining it as a PM, then that is your mean effective pressure. Okay, so basically work for a Carnot, it can also be written as PM into swept volume. Okay, and in this Carnot cycle, the effective swept volume, uh, if you study in these IC engines, those chapters, the effective swept volume is basically this V4 minus V2. Okay, this is your effective swept volume. This derivation is not of your concern, but I'm just giving you. Okay, so PM into V4 minus V2. Okay, and we know the work output for one cycle. We have to calculate PM, which is my mean effective pressure, and we don't know V4 and V2. Okay, now but we can calculate this again. So W is your PM. Now what is V4? V4 is basically your R T4 by P4, isn't it? And this is your R T2 by P2 from simple ideal gas equations. Okay, okay. Now PM, R is your 0.287. Okay, sorry, 0.287. T4 and T1 are same, 293. And your P4, remember this is kilojoule per kg Kelvin and P4 is given in terms of bar. Okay, so you have to convert this bar in kilopascal. Okay, so P4 is 1 bar, that means your 100 kilopascal. And similarly 0.287, and this one is 380.68 if I remember correctly. Yeah, 380.68. 380.68 divided by what is P2? P2 is 10 bar, that means 1000 kilopascal. Okay, 10 into 100, that is 1000 kilopascal. Okay, and we already calculated W for one cycle, 17.706. 17.706. Okay, now let me put everything here. 17.706 is equals to PM into what this one will be, 0.287 into 293 by 100 minus 0.287 0.73 0.7316. Okay, and from here you will get Pm is your 24.20 kilopascal, and if you want in terms of bar it will be 0.24 bar. Okay, so this is your mean effective pressure. Okay, okay, then let us move to the okay, any question left? We have also done the mean effective pressure. Fine. Okay, then let us move to the next question. Two Carnot heat engines in series, okay, between source temperature and sink temperature 600 and 300 Kelvin respectively. If both the engines develop equal power, determine the intermediate temperature. Okay, so these are very important and easy questions. Okay, so I will do the general formula and then we can directly put it here. Okay, and say this is the another third one. Okay, so there are two Carnot heat engines. Say this is my engine 1 and this is my engine 2. Okay, it is taking out Q1 amount of heat, rejecting Q2 amount of heat, and doing W1 amount of work. Okay, similarly taking Q2 amount of heat, the entire heat it is taking, and doing W2 amount of work and rejecting Q3 amount of heat. Okay, this is T1, this is T2, and say this is my intermediate temperature T. Okay, so now what we can write is that see this T1 is 600 Kelvin and this is I will not go for details here. Now since this is a Carnot engine, I can write eta 1 is equals to 1 minus T2 by T1. Okay, and in general we also know that this eta 1 is nothing but W1 by Q1. Okay, similarly my eta 2 is what 1, oh I'm sorry, this is not T2 by T1, this is T by T1, T by T1. Okay, this temperature is T and this temperature is T1. Similarly eta 2 is 1 minus T2 by T, okay, which is your W2 by Q2. Okay, this is my equation 1, this is my equation 2. Okay, now what it is telling that these two develops equal power. What is the meaning of this? The meaning is that W1 is equals to W2. This is my equation number 3. Now if I divide 1 divided by 2, what will I get then? I will get 1 minus T divided by T1 is equal to 1 minus T by T1 divided by 1 minus T2 by T is equals to W1 will get cancelled. This will be equal to basically Q2 divided by Q1. Okay, and we know that for a Carnot engine the ratio of the heat rejected and accepted by the reservoir is basically the ratio of the temperature of the reservoirs. Okay, so this will be 1 minus T by T1, 1 minus T2 by T will be equal to T2 by T1. Okay, this is from the general Carnot theorem. Okay, so now just have to cross multiply it. So this will be T1 minus T1 into T by T1, and that will be equal to T2 I'm sorry, Q2 by Q1 Q2 by Q1. Q2 is the temperature for T. Okay, so actually this confusion gets created because it's a is a I mean the normal heat engine, this temperature I take it as T2, that's why. Okay, sorry for the inconvenience. Now this is T by T1, so that will be T into this will be your T into T minus T into T2 by T. Okay, so this got cancelled, this got cancelled. So what I got here, T1 minus T is equals to T minus T2. Okay, so from here what I get, 2T is equals to T1 plus T2, and from here I get T is equals to T1 plus T2 divided by 2. So that means if two heat engines are connected in series in such a way that the power developed is same, then the intermediate temperature is nothing but the arithmetic mean of the two temperatures of the source and temperature of the sink of the two engines. Okay, and what is the temperature here? 600. And what is the temperature of the sink for the second reservoir? It's 300 divided by 2, so 900 divided by 2, this is basically my 450 Kelvin. Okay, fine. Let us go to the next question. Two heat engines X and Y of same efficiency. Okay, the other case it was same output, now it is same efficiency, and they are connected in series in such a way that the sink of X works as the source of Y. Okay, now X receives heat at 900 Kelvin and rejects some heat to the sink at T, and then in turn Y rejects heat to its sink at 400 Kelvin. Okay, now they have named the heat engines and X and Y, nothing else. This this heat engine they have named it as X. Okay, it is taking some amount of heat Q1, rejecting some doing some work W1, rejecting some heat Q2, and to a reservoir which is at temperature T, and then same this Q2 amount of heat is taken by your next heat engine Y, which also does some amount of work W2, and then it releases Q3 amount of heat to a reservoir which is at 400 Kelvin. This is, let me say this is T2, and this is your T1 at 900 Kelvin. Similarly, just the previous one, just they have named it. Now once again, since these are heat engines, okay, and so now eta 1 will be equal to what? 1 minus T2 by T1, T2 by 1 minus T by, always getting this confusion, 1 minus T by T1, and eta 2 will be equal to your 1 minus T2 by T. Okay, now what it is telling, that the efficiencies are same. Since efficiencies are same, are equal, what we can write, eta 1 is basically equal to your eta 2, and if eta 1 is equal to eta 2, we can write as 1 minus T by T1 is equal to 1 minus T2 by T. Okay, 1 got cancelled, negative I can positive, I can make it as positive, so I will get, I think, T square is equals to T1 into T2. Okay, so that means your T is equals to root over T1 into T2. So if they have same efficiency, then the intermediate temperature is basically the geometric mean of the temperatures of the source of the first engine and sink of the second engine. Okay, so this will be basically 900 into 400. Okay, so it is 600 Kelvin. Okay, so if the power output is same, it is the arithmetic mean, and if the efficiencies of the two heat engines are same, it is the geometric mean. Okay. Next, two Carnot cycles, a heat engine and a heat pump are combined as shown. You have to check whether this process is feasible or not. This diagram is shown. Now you have to check whether this process is feasible or not. Now for feasibility, whenever they ask you anything about feasibility, you always have to check the delta S universe. Okay, and delta S universe should always be greater than or equal to 0. If it is equal to 0, it is a reversible process, and if it is greater than 0, it is a irreversible process, because entropy of the universe can never decrease. Okay, so this thing you have to check whether this process is feasible or not. So now let us start from this part, heat engine part. Okay, so this heat engine, these are telling us Carnot cycle, so I can directly write this one for heat engine. Okay, what I can write for heat engine, 1 minus 300 by 400 sink temperature divided by source temperature is my efficiency, which is nothing but W divided by 300. W is my output and this is my input. Okay, from here I will get W. Okay, this will be basically 100 by 400 is equals to W by 300. Okay, so this is your 300 divided by 4. Something is wrong. Oh, W divided by 200, I'm sorry. Okay, so 300, what I am doing, yeah, 200 divided by 4, 50. Okay, so my W is 50 kilojoule. Now if my W is 50 kilojoule, this amount of heat that is rejected I can calculate. This is basically 200 minus this one I have got as 50. Okay, so 200 minus 50, this will be basically my 150. Okay, so my this Q2 for the heat engine is basically your 150 kilojoule. Okay, now first I will make the calculations and then I will check this. Okay, now for heat pump I require all the energy inputs. Okay, so I have W, I have this 75, so what will be this one? Okay, so W plus this one, say Q2 dash, this is my Q2 dash. Okay, W plus Q2 dash is equals to basically my 75. Okay, correct, input is equals to output. So from here I get Q2 dash is equals to 75 minus 50, which is your 25 kilojoule. Okay, so I have got all the energies now. Now when I have got all the energies, then only I can check for this delta S universe. Okay, so for heat pump I will check for the delta S universe. Okay, so that will be equal to delta S source. Okay, that basically the system then surrounding. Okay, delta S source plus delta S sink plus delta S your engine. Now since this engine is undergoing a cycle and entropy is a property, so this delta S engine will be equal to 0. Okay, so delta S source will be what? Source is rejecting heat, isn't it? Source is rejecting heat, so minus 200 by 400, Q equal to T delta S from here. Okay, and the sink is gaining heat, 150 by 300. Okay, So this is also half, this is also half, this is equals to 0. So if it is 0, it is reversible process. So we just need to check whether it's feasible. Yes, the heat engine is feasible. But not only heat engine, the heat pump should also be feasible, then only the entire process will work. Same delta S universe, this will be equal to delta S source plus delta S sink. Okay, so for here now this will be my source. Now this source is rejecting heat, so minus 25 divided by 300, and it is giving heat to this sink at 500 Kelvin, and this sink is accepting heat, so that will be 75 divided by 500. Okay, so 75 divided by 500 minus 25 divided by 300. Okay, so I am getting a positive value 0.067 approximately kilojoule per kg Kelvin. Okay, now since delta S universe is greater than or equal to 0 for both the cases, so that's why this process is, or this entire cycle is possible. So entire combination is possible. Okay, then let us move to the next part. In this figure, there is a heat engine HE, and it is working between two reservoirs as shown. The amount of heat rejected Q2, okay, it is rejecting some amount of heat Q2. This is drawn by the heat pump again, okay, and then the heat pump receives the entire work. Okay, this also receives the entire work, fine, of the heat engine. Now if the temperatures are such that T1 is greater than T2 and then T3, okay, then what is the relationship between efficiency of the heat engine and coefficient of this one of the heat pump? Fine. Okay, so eta for the heat engine, what can we write this one as? Output by input, and what is my output? My output is basically W, and what is my input? My input is basically Q1, correct? Okay, then similarly, what is the coefficient of performance for the heat pump? It is again output by input, that is the desired output, and heat pump desired output is this Q3. Okay, so this is Q3 divided by W. Okay, now what I can do is that from the heat pump, the energy balance, if I will do, what I will get, say this is equation 1, I have to find a relationship between these two now, and say this is equation number 2. Okay, so now for the heat pump, sorry, for the heat engine, okay, Q1 is what? W plus Q2. Okay, and for the heat pump, Q3 is also equal to W plus Q2. Is it correct? Q1 is equals to W plus Q2, and here also Q3 is W plus Q2. So from these two equations, from 3 and 4, what we got? We got Q1 is equals to Q3. Now see in these two expressions, W are the same, only difference is Q1 and Q3, and again we got Q1 and Q3 are the same. So eta heat engine is W by Q1, and COP of heat pump I got as Q3 divided by W, which I also can write as Q1 by W, since Q3 is equals to Q1. So see, this is basically the inverse of heat engine. Okay, so what is the relation I got? Therefore relation is nothing but COP of the heat pump is basically inverse of the efficiency of the heat engine. Okay, if you follow this configuration, fine. Next, a solar collector. Okay, a solar collector receiving solar radiation at the rate of 0.6 kilowatt per meter square transforms it into the internal energy of a fluid at overall efficiency of 50%. The fluid heated to 350 degrees Celsius is used to run a heat engine which rejects heat at a 313 Kelvin. The heat engine is to deliver 2.5 kilowatt. What is the minimum area of the solar collector required? Okay, so what happens that there is a solar collector. Okay, so this is my solar collector. It has some area, say this area is A, let us assume, because we have to find the area of the solar collector. Okay, and it gets heat at the rate of 0.6 kilowatt per meter square. Okay, this much solar radiation it is getting, okay, per meter square. Now it transforms this amount of heat to internal energy of the fluid at an overall efficiency of 50%. That means 50% of this whatever it is received, it is used to increase the internal energy. Okay, so energy that is used to increase the internal energy increase internal energy of the fluid is what? 0.6 into 50%, that is 0.5. 50%, na? Yeah, 0.5. Okay, that is 0.3 kilowatt per meter square. Okay, now this much amount is used to increase the internal energy of the fluid. Okay, now this fluid, the fluid is heated to 350 degree Kelvin and it is used to run a heat engine. Okay, now for a heat engine, what happens now? The basically is that the source is basically filled with fluid. Okay, and this fluid has a constant temperature of 350 Kelvin maintained. Okay, so this is the fluid, and this fluid's internal energy is being heated by 0.3 kilowatt per meter square. Okay, this fluid is getting heat in the rate of 0.3 kilowatt per meter square. Okay, and say it is used to run this heat engine, and this heat engine it delivers 2.5 kilowatt power. Okay, it gets Q1 amount of heat, rejects Q2 amount of heat. Okay, and it rejects heat to 313 Kelvin. Okay, this is the entire setup. Solar collector is getting heat. Now this heat, 50% of this is converted to increase the internal energy of the fluid. Okay, then Q1 amount of heat if it is taking, then it will do 2.5 kilowatt of power, and then it will, so what is the minimum? So if you want to calculate the minimum amount of what you call area, okay, so then see, this is the amount of heat input. So if you want to maintain a constant temperature, whatever heat is you are getting inside, if you want to maintain a constant temperature, you have to reject that much amount of heat. So this is also your 0.3 kilowatt per meter square. Okay, now see, this is kilowatt per meter square. If you assume the area to be A, then if you multiply this with A, what you will get? You will get 0.3 into A kilowatt. Okay, so this much amount of heat is the Q1. You understood how it is Q1? See, 0.6 kilowatt per meter square it is getting from the sun. Out of this, 50% is getting converted to increase the internal energy of a fluid, and that fluid is maintaining a constant temperature of 350 Kelvin. Now if it is getting 0.3 kilowatt per meter square, so it has to reject that much amount of heat, then only steady state will attain. So that's why this Q1 is taken out from this heat engine, which is used to produce 2.5 kilowatt. Okay, so now that means eta, it is very clear to us, it is nothing but 2.5 divided by 0.3 into A. Now hang on, we cannot calculate area by this. Why? Because we don't know any other informations. We are given temperatures, but it is not telling us that this heat engine is your what you call this heat engine is your Carnot heat engine. But they are telling us you have to calculate the minimum area. So if you have to calculate the minimum area, so then what will be your maximum efficiency possible? That is your Carnot efficiency. Okay, and what is your Carnot efficiency? Is nothing but 1 minus T2 by T1. Okay, so we just equate these two in order to calculate the minimum area. Okay, so we just equate these two. 1 minus, what is my T2? 313, and my T1 is 350. Okay, 1 minus T2 by T1 is basically your 2.5 divided by 0.3 A. Okay, and from this we will get the area value. Okay, okay, so if you put all the values, you will get your answer as 83.33 meter square. Okay, next. Okay, next let us move to a heat transformer is a device which transfers a part of the heat to supplied at an intermediate temperature at a higher temperature reservoir, while rejecting the remaining part of the heat to a lower heat temperature. Suppose this is my heat transformer. Okay, heat transformer, they are just defining this. A heat transformer is a device which rejects some part of its heat to a higher temperature reservoir, okay, and some part of its heat it rejects to a lower temperature reservoir. Okay, say if this is the temperature T2, this is the temperature T1, this is the temperature T3, then T1 is greater than T2 is greater than T3. Okay, this is how a heat transformer works. Okay, now it is telling us that in such a transformer 100 kilojoule of heat is supplied at 350 Kelvin. That means condition is now T2 is equal to 350 Kelvin, and from somewhere it is getting 100 kilojoule of heat. Okay, from somewhere it is getting 100 kilojoule of heat. Fine. Now what is the maximum amount of heat in kilojoule that can be transferred to 400? So let us what is some amount of Q it is transforming to this source at the temperature T1, then what will be transferred here? 100 minus Q. Yes or no? Correct? No, you have to transfer 100 minus Q. Now since they are telling us the maximum amount, so in case of maximum amount, this all processes should be reversible, and when the processes are reversible, the amount of heat that is rejected or that is accepted by, say this one I am assuming as QH, and this one I am assuming as Q low. Okay, the lower reservoir and the higher amount of reservoir. So this will be if Q the for maximum heat rejected to high temperature reservoir, what will I get? QH by Q low is basically your T1 by T2, which we already know that whenever you have to do for maximum possibility or the Carnot possibility, you have to basically do the ratio of the heat accepted and rejected is basically the ratio of the temperatures. Now What is the maximum amount of kilojoule that can be transferred to 400 Kelvin reservoir, so that rest heat is rejected to 300 Kelvin reservoir? Okay, so what we got then, QH by Q low is basically your 400 divided by 300. This is your 4 by 3. Okay, now this 100 kilojoule part is only getting transferred to QH and Q low, yes or no? So what we can write, that QH plus Q low is equals to your 100. What we need to calculate? We need to calculate QH, yes or no? So we will express QL in terms of QH. Okay, so QH we kept as it is. From this equation we get QL is equals to 3 by 4 times QH. Okay, so this will be your 7 by 4 times QH is equals to 100. Okay, and from here 400 divided by 7, so you will get basically QH is equals to your 57.14 kilojoule. Okay, okay, next let us come to the last question, the gaseous nitrogen. Okay, so gaseous nitrogen cycle operates on a Carnot power cycle, which is the which the perspective volumes of the four corners, starting with the volume at the isothermal expansion, this one blah blah blah, this V1 V2 V3 V4, these are given. The power received by this one is 21.1 kilojoule of heat. Now sorry, the power cycle receives 21, that means heat added to the cycle is given to us as 21.1 kilojoule. Now you have to determine the net work done. Okay, we already know how the PV diagram looks, but whenever these values are given, we just have to draw these two cycles, isn't it? So we have already done these things. Slopes are same since I am drawing it, pardon me for okay, fine. Okay, so now we know V1 isothermal expansion is this one, so we know V1, so V1 is 10.1. okay, the starting point is your isothermal expansion, that's why I have started the point 1 from here. Okay, 10.1 liter. Your V2 is given as 14.53 liter. V3 is given as 226.54 liter, and V4 is given as 157.73 liters. Okay, then heat received is given as 21.1 kilojoule. Okay, then what we know, okay, so ln V3 by V2, which we have already done in previous sums. Okay, so 21.1 into 10 to the power 3. Okay, and for nitrogen, if you want to calculate it, this will be basically 8.314 divided by 28 into T2 into ln. Sorry, I have converted this to kilojoule, so I have to multiply this into 1000. Okay, so ln V3 is 226.54 divided by 14.53. Okay, so from here you will get T2 is equals to 25.87 Kelvin. Okay, then next in this process from for the process 3 to 4, okay, TH by TL is equal to V3 by V4 to the power gamma minus 1. Okay, now we assume gamma is equals to again 1.4. Okay, so therefore TH divided by 25.87 is equal to 226.54 divided by 157.73 to the power 0.4. Now from here TH is equal to 29.901 Kelvin. Okay, now therefore heat transferred in 1 to 4 is your Q1 to 4 is your RT ln V1 by V4. Okay, so you put it here, so you will get here minus 8314 divided by 28 into 29.901 into ln 10.1 divided by 157.73. okay, this will be your 24.401 kilojoule. Okay, so therefore net heat transferred is what? Minus 21.1 plus 24.401 kilojoule. Okay, so you'll get this one as 3.301 kilojoule. Okay, now therefore we know that for a cycle W net is equals to Q net, and we have got Q net, so this W net is nothing but 3.301 kilojoule. Okay, so with this I conclude today's class. Okay, so if you have any doubt, you can ask me or you can mail me later on. Okay, yeah, so yes, thank you.